In this session we'll design reinforced concrete wall footing, as you can see from this diagram, and we are given the following information. Thickness of the wall is 20 inches and the dead load is 26 kip per square foot or per foot length, same thing. The live load is 20 kip per foot length, and the bottom of the footing is 6 feet from the grade. We have the concrete strength is 4 kip per square inch or 4,000 pound per square inch. The steel is 60 kip per square KSI, and the bearing capacity of soil is 5 kips per square foot or 5,000 pound per square foot. So what we'll do here is, the easiest way is we'll go with the step-by-step procedure mentioned in your book or the notes. Let me just show you how we'll follow that. So you see, step number 1 here is calculate the estimated thickness of the concrete, and we use this equation, and we'll use these equations as we go. So we'll go step by step here. So step number 1 is calculate the estimated thickness of concrete. So meaning we have the task of doing this part first. So we'll write, and I suggest you do the exact same thing when you do the design, be it in the assignment or in the test. So it is calculate the thickness of footing, which is in our calculation is called H. So to do that, we have in the procedure, if you look here, you have A is B, you calculate B. This is the equation for, let me see if I can get this. This is A and this is B. So we need to do this. So A is, we'll do A. So A is B minus T divided by 2 is equal to, and just again double check. So B is equal to DL divided by QA. And just A, so we have B is equal to dead load plus live load divided by QA. Of course, this is an equation, so I will just purple these ones so that you know these are equations. And by the way, you can during the test you can bring this entire steps. We have 6 steps here. You can bring them with you to the test or assignment and do the entire. Just follow the steps and you should be fine, because the design most of the time is straightforward. So here's step number 1. There you go. So we need to calculate now B, which is dead load live load divided by QA. Then B is H, which should be minus T divided by 2 multiplied by half. So I'll do the numbers here. So is equal to dead load is given as 26 plus live load is 20, and by QA is equal to 5 kip per foot, and is equal, so the answer for this is equal to 9.2, that is foot. I will round this up to 9.5 feet. So you see, as we go, you might ask why 9.5? Make it 9, it's up to you. This is the design. So the design is whatever you suggest, but you go back and check later on to see if your design is okay. So again, the design will be different from one student to another, from one engineer to another. Now the second is calculate the estimated thickness. Which is H. Because after all, you need to work, this is what we're trying to do. Okay, so the equation for H is equal to B minus T divided by 2 multiplied by half. Again, this is an equation. So for this we have, just watch for the units, 9.5 feet minus T is given as 20 inches, so 20 inches divided by 12 to convert this into feet, and then divide by 2 multiplied by half is equal to, so this will get us an H value equal to 1.95 feet. So this is equal to, if you multiply this by 12, then this becomes 23.5 inches. So we'll say use 23 inches for H equal to H. So while we are on it, we might as well also calculate the value of depth, because you know, here we have, let me just sketch the reinforcement. The reinforcement would be somewhere something like that, and I need to do this. This is the cover and this is the depth. So I need to know both the depth and cover, and we say the cover is, we will use the cover as equal to 3.5 inches always. Okay, we have proven this from the previous building code. We said the clear cover is 3 inches, and we add half an inch for the reinforcement. So here I would be tempted to do the depth. The depth will be equal to 23 inches minus 3.5 inches is equal to, so that would be equal to is 19.5 inches. That is the depth. So again, circle this one and circle this one, and while we have done the H, because you know, again, maybe I should do this also. So you have this distance. This is called H1 and this is called H. So I'm going to need this one. So now I know H value is given. I calculate the H value here. So I would like to calculate also the H1 value. H1 value is equal to the entire depth, which is 6 feet here, 6 feet minus the H value, which is, I'm not going to use 1.95 because I used 23 inches, so I would say 23 inches divided by 12. That is exactly will give me the value. So it will be 23 divided by 12 minus 6 is equal to, so I get 4.03. 4.083 feet. So I got these values all. So I can update this one is equal to 4.083 feet, and this is equal to 23 divided, yeah, it is 23. I don't know, it's 23 inches. So that is step number 1. So I got the values of the H. Now let's go to another page. So now we go to step number 2, and step number 2 says, step number 2 is calculate the net soil pressure, and this is the equation for it. So net QE is equal to QA minus H. Okay. So step number 2. Let's calculate the net soil pressure. Which we call QE. And for QE, the equation, if you look at the equation of QE, is equal to QA minus soil density multiplied by H1 minus concrete density multiplied by H is equal to. And again, this is a fixed equation. And if you want, you can always consider this to be 100 pound per cubic foot, and this to be, sorry, this is concrete is 150. So this is equal to this is an equation. So here is the equation, and the concrete is always 150 pound per cubic foot, and the soil is, we'll use in our calculation because they are different in reality, but for the sake of just this course, we'll keep them fixed, and this is 100 pound per cubic foot, because the soil investigation will tell you what is the density of soil. And same thing for concrete, you need to choose certain type of concrete. Anyway, so to calculate this, QA is equal to, it is 5 kip per square foot minus, now you see the soil is 100 pound per cubic foot multiplied by the H1, which is, we calculated this to be 4.083 feet in the previous, and the concrete is 150 pound per cubic foot multiplied by H is equal to 23 inches divided by 12 is equal to. Now we have some sort of conversion here we need to do, and you have to pay attention to this. Now you see the units here are mixed. So if you look at, this is kip here and these are pounds. So you want to make sure that these can be consistent. So what I do is I need to convert this to, this becomes 5,000 pound per square foot, because each one kip is equal to 1,000 pound, and minus, now this will be in pound, everything will be in pound, minus pound per cubic foot multiplied by 4.083 feet minus the concrete is 150 pound per cubic foot multiplied by the height is 23 point, so 23 divided by 12, 23 divided by 12 is equal to 1.916 feet is equal. So if you do the cancellation of units, you see foot and foot will be cancelled, foot and foot will be cancelled, so we'll get pound per square foot, so the units are consistent in this case. So the value here will be equal to, the answer meaning will be equal to 4,304 pound per square foot. If you divide this by 1,000, it becomes 4.304 kip per square foot, or we call it kip SF. Kip. Okay, so this is step number 2. Now step number 3, again you go by the rules because that is what will be easier for you and for all of us too. So we are done with step number 2. So you see step number 3 is calculate the width of the footing. So if you look at here, this is the equation: B is equal to DL plus LL divided by QE. So I'll do that. So step number 3, calculate the width of the footing, and that is B. So if you want, this is what I'm trying to do. And the equation for that, B is equal to dead load plus live load divided by QE, and this is again an equation is equal to, so we have 26 plus 20 divided by 4.03, sorry, 304. is equal to, so this is equal to 10.68 feet. I will round this up to 11 feet. So these are the, so if you look at the previous process so far, we managed to calculate the so we managed to calculate the thickness of the footing, and so we did. So now we have this part is, we calculate this part to be 11 feet and this part is 23 inches. That is the first stage in which we said the measurement is what we needed to calculate. So I'll continue with the steps. So now step number 3, let's see what our step number 4, sorry, is calculate the factor soil pressure. Now this stage will will isolate the cantilever part of the footing. We're in the process of calculating the reinforcement. So for reinforcement we'll use the ultimate strength design. So for the ultimate strength design we need to do factoring of loads. It's 1.2, 1.6, that's what we're trying to do. And we'll use this equation to get the factored load. So let's go back to our, so here step number 4. Is calculate the factored soil pressure. Now we said this is the reason for this is excuse me, I'll treat this as if it is a cantilever, as only half of the footing is. So this is what I'm after. This is the QU, and of course this will be the distance, which we will call uppercase D, so D1, So let's do one step at a time. So the Q U is equal to, according to the equation here, 1.2 dead load multiplied by 1.2 dead load plus 1.6 live divided by the width. So this is 1.2 dead load plus 1.6 live load divided by B, and that is again an equation. So back to, so I have 1.2 and dead load is equal to 26 plus 1.6 and live load is 20 is equal to 20 divide by the width, and the width is equal to 11 feet is equal to, this will get us to 5.745, that is kip square foot. So if you want, you can mark this as about 5.745 KSF. So now that we have this value, we need step number 5 says that you need to check the now whatever we suggested previously will need to be checked now. So let's go to another page. So if you go back and look at the steps here, say step number 5, over step number 5, what does it say? It says check the shear force capacity of the suggested footing at distance of D. So it says you have to check the shear force capacity of the suggested footing at distance of D from the face of the wall. And these are the equations for them. So what it's trying to do here is, would like to see what is the maximum value of shear. So let's go back to our, meaning that we have this is the beam, and this is the QU, which is equal to 5.745 kip per foot or per square foot, same thing. Now, according to the building code, it says the maximum shear happens at distance of D from the face of the wall. This is maximum shear location, or they call it critical shear section. And this happens at distance of D. A distance of D from the face of the wall. So I need to calculate the shear at this point first, and then after that compare it to the concrete shear capacity. Now first of all, what this distance, I need to know what is this distance, because I will need this distance. And this distance, let's call this distance as D1. So now to step number 5. Step number 5, it says is calculate maximum shear force at distance D from the face of the wall. For that I need the distance D1, so D1 is equal to, again if you go back to the rules, you'll see D1 is defined here as B minus T divided by 2 minus D. So is equal to B minus T divided by 2 minus D. And this is again rule. So B is equal to, we said 11 feet. T is equal to 20 inches divided by 12. Everything is divided by 2, and all of it is minus D, which is 19.5 inches is equal to. So from this we get the value of D1 in feet, which is equal to 3.04 feet. Okay, what is next? Next we'd like to calculate the shear force at this point. And the shear force at this point is equal to, let's go back to the rules. VU, we call VU is maximum. VU is shear force is QU multiplied by D. So VU, now let's say calculate VU, which is the maximum shear force, which is here at critical shear force section. And the equation for VU is equal to QU multiplied by D1. Again, this is an equation. So now we have the value of QU and D1, so we can calculate the VU. QU is equal to 5.745 kip per foot, multiplied by D1 is equal to 3.04 feet is equal to, so we get the value of this one equal to 17.46. that is kips, because foot will be cancelled out, this one and this will be cancelled out. So this is a value of, now I need to calculate the concretes. I need to calculate suggested concrete's shear force capacity, which we call Vn. And the equation for Vn is from the ACI, the American Concrete Institute, is equal to phi multiplied by 2 multiplied by square root of FC prime and PSI multiplied by B multiplied by D. Now I'm going to simplify this so that you'll not be confused with it. So Vn is equal to, phi will be always 0.75, so 0.75 multiplied by 2 multiplied by this FC prime, and B will be always 12 inches, and then D. So this will lead to, just trying to make the equation as simple as possible, so now we'll simplify this even more. So it becomes Vn is equal to 0.7 multiplied by 2 is equal to 1.5, and this is FC prime, which will be in PSI always, multiplied by 12 inches and multiplied by the depth. So this will be always the equation. Now let's go and simplify this. Is equal to is 1.5 multiplied by 4,000 as pound per inch square, multiplied by 12 inches, multiply the depth is 19.5 inch from our calculation. And if you look at the units here carefully, you'll see this is inch and this is inch. We'll go with this inch square, so we'll be left with pounds. And the value that we'd like to compare with is this one, which is in kips. So we might as well at this stage also divide by 1,000 to convert this into kips. Is equal to, so I get the value is equal to 22.2 kips. So this is the capacity of concrete. The suggested thickness 23 inches for H will give us a capacity of shear equal to 22 inches, and the actually applied shear is equal to 17, meaning so 17 or 17.46 17.46 kips being less than the 22.2 kips is actually a safe design, is okay, or safe design, because this is actual shear force, and this is the concrete's capacity for shear. Concrete, or maximum allowable, let's put in this word to be easier, I guess, is maximum allowable shear force on the concrete. So the maximum level is being 22 and the applied is being 17.46 is safe design. So this is good. Now once we get this part also passed, then we'll move to another so let's look at the steps here. So once we calculated this, as you can see here, now I'll move on to the next, which is calculate the maximum bending moment. And to calculate the maximum bending moment, here are the rules we need. So we need to calculate the distance, and the maximum bending moment happens at the face of the wall here. So this distance is equal, this is d2, and so we calculate d2, and then after that we go to the equation of the WL squared divided by 2, which is this one, and we calculate the bending moment. So that's the step. So let's do that. So step number 6. And 6 is to calculate the maximum bending moment, and of course on design the reinforcement rebars, or AS if you will. So with this, again, let's do the sketch, because that will make things a bit easier for us. So if we do the sketch, so this is a cantilever, and this is the uniform load, which is QU equal to, and let's do the number for QU is equal to 5.745 cube per foot. Now the maximum bending moment happens at this point, at the face of, so I need to know this distance. We call this distance uppercase D2, and we know the equation for maximum bending moment here is equal to WL squared divided by 2, which is in our case is equal to QU, it stands for W, and L is D2 squared divided by 2. So just keep that in mind. This is what the bending moment is. So first of all, I need to know what is D2, and the equation for D2, again, if you go to the rules here, the equation for D2 is here, B minus T divided by 2. This is one. Here. So B minus 2 divided by 2. So equal to B minus T divided by 2, and B is in this case 11 feet, and T is 20 inches divided by 12 to make it feet, divided by 2 is equal to, so from this we'll get the value equal to 4.67 feet. Now the MU is equal to QU multiplied by D2 squared divided by 2 is equal to, so QU is equal to 5.745 kip per foot multiplied by D2 is equal to 4.67 feet squared divided by 2, so I'll get a value of 62.64, that is kip foot. This is the bending moment. So now we go back to the reinforced concrete beam design, or reinforced concrete design in this case. So now we need to calculate, like I said, we have the following equations to use. MU equal to RU BD square, and then steel ratio equal to area of steel divided by B and D. These are the only two equations that we'll use always in the design. So we need, like we said in the explanation of the lecture, we said we have this value, we know this value, we know this value, this is what we need to calculate, the RU is what we need to calculate, and knowing RU, we'll be able to get the value of steel ratio. We know the steel ratio, we know B, we know D, we'll be able to calculate this guy. That is the task. So let's go back to Clean this first. So we go to, and here we need to pay attention to the units. So mu RU BD square. Mu is we calculate mu to be this guy here, is equal to 62.64, and put the units. Kip foot is equal to, RU is unknown, B is always 12 inches. Don't mix this, so this is always, maybe I'll put a note here, always 12 inches back, and the depth is 19.5 inches. So again, if you would like to isolate RU, is equal to 62.64, and put the units, kip foot like I said, okay, that will serve you better. 12 inch multiplied by, this need to be squared of course, 19.5 inch squared. So if you look at the units here, you have inches here, we have inch, and we have feet here. And if you go back to the tables, or you remember the tables, they are always in pound per square inch, so we need to make everything pound and everything inches. So to convert this into pounds, I need to multiply by 1000. And to convert this into inches, I need to multiply by 12. So now this is equal to, let's see how much we'll get. This is equal to 164.7, that is pound per inch square. So now we go to our tables, because I would like to get the value. So what is the value of steel ratio, knowing that the RU is equal to 164? So let's go back to the tables. Again, these are, so I have a combination of 4000 concrete and 60 steel. 4000 concrete, this is zone. So I have 4000 concrete and I have 60,000 steel, and the value of R, these are the R's, 164 point something. So I'll go to 165. Let me just double check. Yeah, 164.7. So I will go to 165. Where is 165? $63, and this is 168. So 168 is, so the value steel ratio for 168 is 0.0032. So equal to 0.0032. That is from table is 826B. Table that's 6B. But we need to check also the steel ratio. Check this steel ratio. against the minimum steel ratio and maximum. And we do this from this table, same thing. If you go to this table, of course maximum doesn't apply, it always applies for minimum. So for 6,000 steel and 4,000 concrete is 0.0207. that is the maximum. So the hour value is 0.00, so this is maximum. We are not even near that one. We need to check the minimum. So for minimum, I have steel 60,000 and this is 4,000 concrete. So the minimum is 0.0033, which is larger than what I found here. So minimum is equal to 0.0033. This value is greater than what I found, which is 0.0032, meaning that I must use the minimum, because otherwise the reinforcement will have no effect. So use 0.0033 for steel ratio. So that's what I'll be using. Now to calculate the steel, area of steel is equal to steel ratio multiplied by B, which is always 12 inches, multiplied by D. That is an equation. So if you want, you can do this also being an equation. So let's do the numbers. So is equal to, is equal to steel ratio 0.0033 multiplied by 12 inches multiplied by the depth is 19.5 inches, and we get the steel to be equal to now 0.702, that is inch square per foot, because we are designing all of this per foot. Okay, so let's move to the next page. Now I'll continue. Now to get, now we need to understand here, it is not, we'll not be using table A28. We'll use table A29 because we are designing this per foot. So if you go to tables here, and the table A29 is for, see, this is for combination of bars, but I will not need this one, I will need this one. This is what I will need to do. This is area of reinforcement in 1 foot width, so you have to use table A210. In our case, we had a value of 0.7 02 inch square per foot, so probably 0. So if I'll do this, I'll be able to get this guy. Sure. 0.75 is the intersection of number 6 bars at 7 center spacing. See, this is spacing of the bars, and this is the bar number. So it will be number 6 at 7. So we'll say here, use number 6 bars at 7 inch center spacing and this will give us an area of steel equal to 0.75 inch square per foot. That's what we calculate. So meaning, now if you look at the footing itself, so the reinforcement is this is the reinforcement I just calculated. So this is number 6 bars at 7 in center to center. Now to design this bar, we set the longitudinal bars and the equation for these bars also. So the secondary, or we call them shrinkage and temperature rebars, are the secondary ones. Bars. And the equation for the secondary bars is equal to, I'll call it AS2, is equal to 0.0018 multiplied by 12 inches multiplied by depth, always. So this is, use this equation. Now if you put the numbers here, AS2 is equal to 0.0018 multiplied by 12 inches. The depth is 19.5 inches, is equal to. So from this we'll get a value of 0.421, that is inch square per foot. So again, if we go and look for the for 0.421 here, 0. So if I go in 5, so I could do this one. So number 5 at 8 inch center spacing will give me 0.47 because I need 0.42. So that will be a good choice. So I'll say use number 5 bars at 8 inches center spacing. This will give us an area of steel which is equal to 0.47 inch square per foot, which is larger than 0.421 inch square per foot. Okay, so this becomes is number 5 at 8 inch center spacing, and that is the end of our design.